Morning, everyone. Just wait a few moments till everybody comes in. You will have 72 hours for the final exam. I don't know about the starting date, though. If that's the date on the final exam schedule, then yes. Morning, everyone. How are we doing? Questions while we're waiting? Well, actually, there's no reason to wait. It is 7 past 10. Let's say any questions before we begin. How was the midterm? Too easy? Questions, comments? The only tricky question was the last one. And all you had to do was think about it. Right? I mean, it's nice to have one question where you have to think. All right. Oh, it's good. It's good. It's good. It shows that you know things. So some of you understood it but don't know how to prove it. The idea was this. You know how, no, not that, sorry, because I changed it. It was actually a bit harder. The original question was a minus 1 instead of a plus 1. And that made it slightly more difficult. But look at this. No, don't look at that. We're back. We're back to this. Sorry. Back to that. You know, I mean, we saw that in class. Or, I mean, even if we didn't, it doesn't matter. You know that this is a polynomial of degree 3. You know it's not irreducible, right? You can spot a root easily. -1 is a root. So x minus -1 or x plus 1 has to be a factor. And you can do some long division. Blah, blah, blah. This is going to be x squared minus x plus 1. I'll let you do it, but there it is. Right? I mean, we can convince ourselves we get an x cubed minus x squared plus x squared, so that's gone. And then plus x minus x, so that's gone. And finally a plus 1. There it is. What does that mean? That means that if we replace x with a, then x cubed, or I might have something with it, then a cubed plus 1 is a plus 1 times a squared minus a plus 1. But mod a cubed, which is what we're working in, right? Because we're working in z cubed, mod a cubed, this is 0. So we get that a plus 1 times a squared minus a plus 1 is equal to 1. So a plus 1 is invertible. That's it. It was just noticing this. How are we doing? Questions? Right, so it was just, really it was one line. Well, we'll see. We'll see. I mean, this is the easy way to prove it. Maybe there's something else. Maybe there are other ways. Just because you did it a different way doesn't mean it's wrong. There could be other ways to do it. We'll see. Let's not worry about it for now. Today, we're going to talk about Is that right, David? Sorry to hear that. Well, again, let's not worry about it. We'll mark it, and then we'll see, and then we'll discuss. So today we're going to talk about John Conway. John Conway, a very influential mathematician of the 20th century and 21st, who just passed away this past April. He's very well known. Well, I mean, first of all, he rose to fame in the 70s with a game, with a computer game called The Game of Life. Not to be confused with the board game of the same name. What the game of life is, it's a computer program that evolves on its own according to a few simple rules. Let me give you those rules. So rule 1, any live cell with fewer than 2 neighbors dies by underpopulation or by loneliness. Two, any live cell with 2 or 3 live neighbors lives on to the next generation. Three, any live cell with more than 3 neighbors dies by overpopulation. And lastly, any dead cell with exactly 3 live neighbors becomes a living cell by repopulation. So, with just these 4 rules, you start with an initial pattern known as a seed, and you see how life develops. And this gives you a flavor of what Conway is known for. He takes theorems, mathematical theorems, and transforms them into games. Or takes a game and analyzes mathematically what's going on and gets some nice results. This game of life here, there are a bunch of websites devoted to that. And let's discuss that a bit. In fact, there are still results being produced as far as that game is concerned, 50 years later. I've posted a link to the game on my courses. And here's an example of a seed, right? So you start with this, I've posted this link on my courses. And then it evolves in time. You have spaceships and a bunch of things. So you can play around with that. Some sort of spaceship earlier today. Yeah, you've got climbers and gliders and this and that. I mean, there's a whole slew of things. And like I said, there's still new things being developed every day. There's still open questions surrounding this. And, I mean, again, depending on what initial pattern you start off with, you get these results, right? So here this ship is moving forward. All right. But that gives you the flavor. So again, there's a link on my courses to this website if you want to have a look at it. This gives you a flavor of what Conway does. What I wanted to discuss today is the following. Consider, let me just move this out of the way here. Consider the following theorem of Sylvester. From 1884. If A and B are relatively prime, so take two integers that are relatively prime, actually natural numbers. Take two natural numbers that are relatively prime, then A minus 1, B minus 1, minus 1 is the largest integers would have been fine here. Sorry about that. Is the natural numbers. Is the largest natural number. That is not a combination. Let me change that. That is not a sum of non-negative integer multiples of A and B. A theorem which might have gone unnoticed. Right, I mean, well, first of all, what does that even? What does that theorem even say? Let's take an example. If you take two integers which are relatively prime, consider 3 and 4. What is the GCD? Greatest common divisor of 3 and 4, you know that to be 1. In other words, 3 and 4 are relatively prime. What Sylvester's theorem is saying is that 3 minus 1 times 4 minus 1 minus 1, right? So A minus 1 times B minus 1 minus 1, what is that? This is 2 times 3, which is 6 minus 1, that is 5. 5 is the largest integer that is not a combination of 3 and 4. What do we mean by that? Right, so not a sum of non-negative integer multiples of 3 and 4. What does that mean? That means any number bigger than 5 has got to be some combination of 3 and 4. 6 is 2 times 3. 7 is 3 plus 4. 8 is 2 times 4. 9 is 3 times 3. 10 is 2 times 3 plus 1 times 4. Right? A combination, a sum of non-negative integer multiples. And so on and so on. 11. What is 11? 11 is 1 times 3 plus 2 times 4. And so on and so on. Does everybody understand what Sylvester's theorem is saying? I'm not going to prove it, but it's saying that 5 was the largest number, which is not a sum of non-negative integer multiples. Questions here? Well, that's just Sylvester's theorem. What does Conway do? Conway takes this theorem and develops a game. Known as Sylver coinage in honor of Sylvester. What is the game? Two players take turns naming positive integers. That are not the sum of non-negative integer multiples. Of previously named integers. The person to name one loses. Right? Because one describes every integer as a sum of non-negative integer multiples of 1, right? 2 is 1 plus 1. 3 is 1 plus 2, and so on and so on. If you have 1, you can touch all the integers, all the positive integers. Let's illustrate. Let's see what this game actually is. So let's say we have player A and player B. Let's play a fictional game, and then we'll play a game together. Suppose player A starts by choosing a number. Whatever, any number. First of all, he doesn't want to play 1, because then he loses. So any number bigger than 1. Let's say 29. Player B then chooses a number himself or herself. Any number that is not a multiple, that are not sums of non-negative integer multiples of the previously named integer. In this case, there's only one previously named integer. So player B chooses any number that is not a multiple of 29. Let's say player B chooses 7. Very well. Right, it's not, it could have been a number bigger than 29. Could have been 30, 31, 32, and so on. Not 58, right? Because 58 is 2 times 29. And not 87, because 87 is 3 times 29, and so on. And anything that is not a multiple of 29 would have been fine. Let's say player B chooses 7. It is now player A's turn to choose. Player A can choose any of the numbers, except cannot choose 7, because 7 has already been chosen. Cannot choose 14, because 14 is 2 times 7. Cannot choose 21, because 21 is 3 times 7. Cannot choose 28. Cannot choose 29. Cannot choose the sum of these two numbers, 36, and so on and so on. Anything else is fair game. Let's say player A chooses 4. Let's just say, right? since 4 and 7 are relatively prime, we know by Sylvester's theorem that immediately the largest number that is not a sum of non-negative integer multiples of these two, and only these two, is already 17. So without regards to this one, just with these two, already every number bigger than 17 is gone. Why don't we list the available options for player B? What is left for player B? I mean, I wrote 4. I should not, right? 4 is gone because it's already there. 7 is not available. Neither is 8 because 8 is 2 times 4. 9 is still there. So is 10. But 11 is not, right? 7 plus 4 is 11. So that's gone. 12 is not because it's 3 times 4. 13 is still there. 14 is not because it's 2 times 7. 15 is 8 plus 7, so that's gone. 2 times 4 plus 1 times 7. 16 is 4 times 4. 17 is still there. And then that's it. These are the only choices left for player B. Everybody with us? So what is B going to choose? Let's say B chooses 6. So what choices are left for player A? Well, 6 is gone. 6 plus 4 is 10, so that's gone. 6 plus 7 is 13, that's gone. 6 plus 4 plus 7 is 17, that's gone. Only 4 choices left for player A. What is player A going to choose? Well, that's up to you. Let's say player A chooses 3. By choosing 3, 9 is gone because it's 3 times 3. And I guess that's it. So 1, 2, and 5 are left for player B. If player B chooses 2, that also removes 5 because 2 plus 3 is 5, forcing player A to choose 1, and thereby lose the game. Sylvester's theorem essentially guarantees that this game ends at some point. And there it is. Player A has lost. Why don't we play a game together? You start. Somebody give me a number to start off with. 42 it is. As long as I don't choose a multiple of 42, I'm good to go. So 42 is out, 84, 126, and so on and so on. let me choose 7. Your move. What are you going to choose? As long as it's not a sum of multiples of these two, we're good to go. So 7's gone, 14, 21, 28, 15. 15 is good. And again, as long as I don't choose a multiple of these, I'm good to go as well. Let me go with 6. Back to you. So again, I mean, a lot of remaining choices here. Rashad is suggesting 2, but here's the problem in choosing 2. If you choose 2, I'm going to choose 3, and now what's left? By Sylvester's theorem, just looking at 2 and 3, which are themselves relatively prime, the largest number still available is what? 3 minus 1 times 2 minus 1 minus 1. So this is 2 times 1 is 2 minus 1 is 1. 1 is really the only number left, right? 2 is gone. 3 is gone. 2 plus 2 is gone. 2 plus 3 is gone. And so on and so on. Everything's gone except number 1. You are now forced to choose 1, and you have just lost. So let's not choose 2. And I mean, what's the takeaway from this? The takeaway is if you choose 2, you've lost. Similarly, if you choose 3, your opponent can choose 2, and you're again forced to choose 1. So the first person to choose 1 loses, but really the first person to choose 1, 2, or 3 actually loses. Let's not, so you want to stay away from that. So let's forget, let's stay away from 1, 2, or 3. And it's your choice again. Nineteen is 19 possible? 2 times 6 plus 1 times 7. 12 plus 7 is 19. 19 is not an option. 19 is not an option. 24 is 4 times 6. 24 is not an option either. Is 23 an option? All right, 23 sounds all right. 23 sounds fine. Okay, 23 it is. I will choose 5. Back to you. 13. Lilia suggests 13, but 13 is 7 plus 6, so that's not an option. Kamei is going with 8. 8 is still up there. Now, why don't we list what's left? What is left? Right, because it's starting to, we're really narrowing down the options. What is left? Certainly 1, 2, 3, 4. Anything less than 5 is left. 5, 6, 7, 8 is not available. What about 9? 9 is still there. 10 is 5 plus 5. 11 is 5 plus 6. 12 is 5 plus 7. 13 is 5 plus 8. 14 is 7 plus 7. 15 is 3 times 5. You understand that as soon as you have a list of 5 numbers that are out, right? 10 is out, 11 is out, 12, 13, then 14, 1, 2, 3, 4, 5. If you can realize these 5 numbers as a sum of non-negative integer multiples of the previous ones, then you can add a 5 to each of these. And the result will be 15, and 16, and 17, and 18, and 19, which can also be realized as a combination of the previous ones, and so on for the next 5. So as soon as you have 5 consecutive numbers that are gone, everything else is gone. Is that clear, everyone? All right. So you see what's going to happen, right? I'm going to choose 4, thereby removing the 9, because that's 5 plus 4. And now it's your turn to choose. Exactly that. As Jim points out, you have lost. Whatever you choose, if you choose 1, you're gone. If you choose 2, I'm going to choose 3. And if you choose 3, I'm going to choose 2. Either way, that would have been it. Well, Rashad had suggested 4, but it was too late. Shall we play another one? Let me start this time. I'm going to start with 7. Your turn. Flora's going with 5. So immediately, by Sylvester's theorem, six times 4 is 24 minus 1 is 23 is the largest number still remaining. Right? Does everybody see that? Any number bigger than 23 is going to be a sum of multiples of these, right? 24 is 14 plus 10. 25 is 5 times 5. 26 is 21 plus 5, and so on and so on. Why don't I choose 23 for fun? Your choice. Lilia is suggesting A. Do we want to go with that? It's already there. Let's go with it. Why don't we try to list now what's still left? 1, 2, 3, 4. 5 is gone. 6 is still there. 7, 8 is gone. 9 is there. 10 is 5 plus 5. 11 is there. 12 is 5 plus 7, so that's gone. 13 is 5 plus 8, that's gone. 14 is gone, 2 times 7. 15 is gone, 7 plus 8. 16 is 8 plus 8. And that does it, right? Since 16 is gone, we have 12, 13, 14, 15, 16. We have a list of 5 consecutive numbers that are gone. So if you add 5 to those again, everything's going to be gone. So these are the only numbers left. These are the only numbers left. What are we going to choose? My choice? Let me choose 6. I did not want to choose 6. It's too late. I wrote it down. Is 19? 19 is still there. 14 plus 5 is 19. So I chose 6. It was a bad choice. 6 removes that, and it removes 11 as well, because 6 plus 5 is 11. Your choice? Jaden chooses 4. 4 removes the 9, right? Because 4 plus 5 is 9. And now I'm forced to choose one of these and lose. Very well. Very well done. Indeed, 1-1. Is anybody keeping track? Tiebreaker? Let's go with the tiebreaker. Why don't you start this time? Lilia starting with a 4. Let me go with 9. Back to you. Nobody? Are you forfeiting already? 12, Rashad, 12? 12 is actually 4 times 3. So that's out. It's all good. 13. 13 is still there. Very well. Let me go with 5. Right, I mean, Kathy is asking the good question, why do I keep choosing 7? I'll answer that in a moment. Lily is suggesting 23, but 23 is 13 plus 10, so that's out. 6, Jack is suggesting 6. And now maybe we should write out what's left. What is left? 1, 2, 3 is left. 4, 5, 6, 7 is gone. And now, I mean, if I've given you a list of 4 consecutive numbers by adding 4 to each, everything's gone from then on. No, 11's gone. 4 plus 7. Yeah, so now again, I am forced to choose one of these. You will choose the other, and I will lose once again. All right. Well, it was a bad start of 5, so I think good game indeed. So 2 to 1. Let's try another one. Just so that everybody's comfortable with the game, this makes for a nice final exam question. 17 is suggested. Very well. Let me go with 8. Is Lilia suggesting 7 as a follow-up? We can do that. Let me follow that up with 20. And then a 5. Well, now, before I choose, why don't I write down what's left? What is left? 1, 2, 3, 4. 5 is gone. 6 is left. 7, 8 is gone, but 9 is still available. 10 is gone. 11 is gone. 12 is still there. So is 13. 14 is gone because it's 2 times 7. 15 is gone. 16 is gone. 17 is gone, right? 10 plus 7. 18 is gone. 19 is gone. 20. And I think that's more than 5. So everything is going to be gone after that. 13, yeah, in fact, 13 is gone. Thank you. And so is 12, right? Because it's 7 plus 5. And 13 is 5 plus 8. Thank you. Absolutely. Thank you. All right. So that's left. Let me choose 9. So now I'm suggesting 4. I will choose 6. and we see where this is headed. Whoever starts does get an advantage. Absolutely. Absolutely. We're tied to. Seems like a good place to end this. Do we want a tiebreaker? Did I mess it up? Oh. Oh. Well, let's do one last one. You want to start? All right. Maybe I messed it up. Lilia starting with 20. I will counter with a 5. So you understand that every number except multiples of 5 are still open to you, right? Everything except 5, 10, 15, 20, 25, and so on. 13. $47. Why 47? Only because I know it's a possible choice, right? It's actually the choice made possible by Sylvester's theorem, right? The fact that you chose 20 and I counter with 5 essentially removes this, right? Because 20 is a multiple of 5. So we're now really just looking at 5 and 13. And these are relatively prime, and the largest value still left is 47, given by Sylvester's theorem. I'm not choosing 47 for, it's not a strategy here, only to point out that it's still available, but it was the largest number still available. Your choice, 24, which is still available, right? I mean, 13 plus 10 is 23, and 25 is gone, but not 24. Very well. What do I want to counter with? Let me counter with what? 11. No, I mean, we're tied at 2, so you guys are doing very well. I could have countered with a divisor of 24. I chose not to. Let's see what happens. Your choice. What is left? I mean, that's a good question. Why don't we try to list what is left? 1, 2, 3, 4 for sure. 5 is gone. 6, 7, 8, 9. 10 is gone. 11 is gone. 12 is there. 13 is gone. 14 is still there. 15 is 3 times 5. 16 is gone. 17 is there. 18 is gone. 19 is there. 20 is gone. 21, which is 10 plus 11. 22 is gone. 23, which is 10 plus 13. 24 is gone. And now I think I've given a list of 5, right? 20, 21, 22, 23, 24. So that's what's left. Have I made a mistake there? Is anything in the list that should not be there? I think we're good, right? Okay, I think that's it. For 44 and 23 are gone, right? 23 is 10 plus 13, and 44 is 4 times 11. So those are gone. Lilia is suggesting to play 8. So 8 will be gone. What else? 8 plus 11, which is 19, that'll be gone. Is anything else removed? Anything else? All right. What did we say? 12? Is 12 gone? I don't think 12 is gone, Lilia, right? Is 12? I think it's still there. All right. Let me go with 17. Lilia, you're choosing 12. Is that the plan? 12. Very well. Let me go with 14. Jaden is going with 7. Everybody's going with 7. 7 does not remove 9 and doesn't remove anything else after that. Looking good for you, right? Let me remove 9. Right? Now you see it. Right? If you choose one of these, you're in trouble. If you choose one of these, I'm going to pick the other one. And And that's what happens. But it's all good. Very close. Let's call it a draw, indeed. All right, but that's the game. You can play with your friends. Very nice. Now, a question came up, why was I choosing 7? And let's ask the question, what is known about this game? Actually, not that much. What is known about this game? So let's say this, complete winning strategies are known for answering the losing openings. Complete winning strategies. For answering the losing openings. Well, give us your tactics. I don't have any tactics. I just have a bit more experience in playing the game. But just play the game a bit and you'll develop your own tactics. First of all, this is an important observation here. Complete winning strategies are known for answering the losing positions, the losing openings, 1, 2, 3, 4, 6, 8, 9, and 12. Meaning that if your opponent starts with one of these, well, of course, the first 3 are trivial, right? We've already discussed them. Still, we have not answered that question, Arya. Is there a reason why I was picking 7? First of all, notice 7 is not in this list, right? If your friends start with one of these as their opening position, even though I don't know what the winning strategies are, you should be able to beat them. Right? And I mean, apart from 1, 2, 3, the list is very short, right? There are only 5 numbers there. So my question was, what is known about this game? Well, we know this. In fact, we know, so what does this mean? This means that if your opponent chooses one of these numbers, it is known what you should play to counter and win, regardless of what your friends will play next. So complete winning strategies, that's what that means. But more importantly, Hutchings theorem. And that will answer why I was picking 7. Hutchings theorem. Any prime greater than 5, greater than or equal to 5 wins as an opening move. What does that mean? That means that if you play optimally, if you play the best game you're supposed to play, by choosing a prime bigger than or equal to 5, you should win. However, interestingly enough, Hutchings' proof of this theorem isn't constructive. So it's a very nice theoretical result. Nobody knows what the optimal play actually is. Right? I mean, it's not, we don't have a complete winning strategy. We know one exists. If you start with a prime bigger than or equal to 5, you should win. But there isn't a known strategy. So that's why when I start, I'll start by choosing a prime bigger than or equal to 5. That way I've got an advantage. If I play the best game that I'm supposed to, I'm going to win. Now, if anybody is in computer science, if anybody has a lot of programming experience, I haven't found a website which plays this game. So that would be a very nice project. Anybody here in computer science? All right. So play this game with your friends. So if you are in computer science and you have time, email me. We can discuss this, and I can actually pay you very little money to set up a website. This can be a 1 or 2 semester ongoing thing. We can work something out. What I wanted to mention, play this game. You know, I mean, again, experience is what you want with this. Play that game, and I wanted to discuss in the few moments remaining another game of Conway, known as Conway Checkers, or sometimes referred to as Conway's Soldiers, but I prefer the. All right, so if a few of you in computer science are, or you know, you don't have to be in computer science as long as you have programming capabilities, email me. We'll see what we can do. Conway Checkers. What is Conway Checkers? Well, imagine a checkerboard. Imagine an infinite checkerboard. You know what a checkerboard looks like? Well, in fact, let me not draw it, because there is a website for Conway Checkers. So Conway Checkers, imagine an infinite checkerboard where, right, so we have an infinite checkerboard, infinite in all directions, right? Left and right, up and down. And now draw a horizontal line. Draw a horizontal line, and that's represented by the change in color between the lower half and the upper half. So you draw this horizontal. Well, suddenly you're on the first level above the line. Can we get to a second level? Well, if you took this one and went to there, you jumped over a checker, and now jump over that one, you're now on the second level. You are 2 levels above the line. Can we get to a third level? Can we get right here to level 3? Well, if you do that, and you do that, and then you jump over, and again, boom, level 3. So you get the idea. You have infinitely many checkers at your disposal. Can you get to level 4? Can you get to level 5? Obvious questions arise. And I've given you a link to the Conway Checkers website. Immediate questions arise. First of all, how high can you go? Is there a limit? How high can you go? Second question, what is the minimum number of moves or minimum number of checkers needed to get to each level? 2 very interesting questions. And interestingly enough, they're both answered in the same way. We'll see that on Wednesday. Questions in the meantime? Anybody? Well, thank you all for coming, and I will see you on Wednesday.